All right. I just set the recording, so I'll send that out as well after. But I say we get started. Thank you everyone for joining today. We're excited to have our second meeting, I think, for this committee. So we're off to a decent start, and we have our Energy and Water Nexus scheduled for September. So this will build upon probably at that event and in future discussions. So with that, I'll turn it over to Les, one of the committee co-chairs, to give the introductions of the speakers.
Well, thanks, Cameron. Thanks for the chance of actually moderating three presentations. I've been looking forward to this, the promulgation of the D.WRE regulations. It's extremely important for California water because we don't have enough of it. And so IPR and DPR is extremely important to us. So thanks, Cameron, for organizing the presentations, the three presentations. First, we're going to have an overview of DPR regulations by Robert Brownwood, and then we're going to have a industry perspective by Val Frenkel, PhD. Thanks, Val, for joining us. And then we're going to have Dr. Leila Khatib of San Jose State University to talk about the treatment and AMR testing in wastewater. So first and foremost, thank you, Robert, for joining us and talk about the regulations from a state board perspective. You are currently the Division of Drinking Water Assistant Deputy Director in the Program Management Branch, responsible for Recycled Water Program, the Regulations Development Program, the Laboratory Accreditation Program, and New Treatment Technologies Program. Robert, you've also worked to see this career dream of yours fulfilling the promulgation of Direct Potable Reuse regulations and helped potable water projects in Mexico, Guatemala, and Brazil. So please tell us all about the state board's regulations. Thank you.
Thanks, Les. Welcome everyone. I won't say everything about it because there's a lot. And as far as my dream, when I first started engineering, I was thinking more that I'd be on the valve side of the house and not writing the regulations, but actually designing treatment. But that's okay. Without the regs, we probably wouldn't be able to do the design. So go ahead, Cameron, if you can go to the next slide, please. Go ahead and jump right into this. This is kind of a brief history of the three. There's more than three legislative bills. There's a couple Senate and Assembly bills, but the first one was the indirect potable reuse, and we had a deadline of December 31st, 2013. And I came back to California, managed the Tulsa water system for 10 years, and I came back right into early 2014. And at the time of the DPR or the IPR regulations, which most of you know, the drinking water program is still within the California Department of Public Health. In July 2014, we go over to the State Water Board, and surface water augmentation regulations were adopted pretty shortly thereafter, 2 years later. And the DPR regulations, as you more than likely know, were adopted last year in December. They were adopted by the board. They're currently in the Office of Administrative Law being reviewed, and if that goes through okay, no changes required, then they should be ready to go October 1st of this year. There's currently 22 active groundwater projects and 11 proposed. There's 2 surface water augmentation projects with 2 proposed, and then there's 5 DPR projects that are just kind of waiting for the regs to see how they go, and those will be started shortly thereafter. Just for those who don't know, every position within state employment needs to be approved by the Department of Finance, the legislature, and the governor approves the overall budget. So every position has a duty and reason that they exist. The DPR regs is a legislative mandate that we write these regulations. So we are not given any positions to do the regulations, but fortunately we have some really excellent staff. Jim Chow, particularly, we just wanted to see DPR regs through, so we diverted resources to get these regs finished. Next slide, please. There, so there's multiple types of reuse, as you're aware of. There's groundwater, recharge, surface water augmentation, and then there is this direct potable reuse. Within the direct potable reuse, that was created back in 2010, Senate Bill 18 directed the Department of Public Health to go ahead and see if it was even feasible to establish direct potable reuse criteria. And then we created an expert panel. The expert panel in 2016 said, yes, it's feasible to adopt direct potable reuse regulations as long as you conduct some research projects. There's about 6 research projects that they recommended before the regulations were finished. So we went ahead and did that research. And then in October 2017, Assembly Bill 574 defined direct potable reuse. Still read that definition that they provided, because the planned introduction of recycled water either directly into a public water system or into a raw water supply immediately upstream of the water treatment plant. And then that same bill mandated that the water board adopt our D.WRE regulations by December 31st, 2023. So in the development, when we first started looking at the definitions and what they meant, the statute didn't define what even a water treatment plant was. They also didn't define what a raw water body was. So we realized that surface water, we assumed, and everybody assumed as well, that it was not written in statute, that it was like a treatment plant, surface water treatment plant. In reality, as many of you know, a treatment plant could be anything from a chlorination facility to even a fluoridation facility on a single well. So we had to make the decision early on that we were going to just go ahead and define regulations, create regulations for not only raw water augmentation, which is what was required by December 31st by the statute, but we were going to go ahead and write regulations for treated water augmentation as well. And then next slide, please. So as you can see, surface water augmentation, raw water augmentation, there is something between the raw water, the raw sewage, and the distribution system. Something in between is a series of pipelines or conveyance systems, could be a reservoir, but it's before a drinking water treatment facility, and then it goes into the distribution system. And we, again, like I said, even a groundwater situation could be, right? We knew that there's places like Fresno and Clovis and Central Valley that had these recharge basins, that right next to these recharge basins could be potable well. So we really were cognizant on that fact and created our regulations. And once these regulations are through and done, people interpret them and look at them, apply all kinds of different scenarios to meet the regulations and the statutes. And aware of definitions for public water systems. Even though those have been around for years and years, you're still the challenges to exactly what is a public water system. Does my system meet the definition? So we're aware of that going into the development of our DPR regulations, try to account for every scenario that possibly could be out there. Next step, please. And then treated water augmentation is you just take everything out from the wastewater plants to the drinking water distribution system. There, when I say wastewater plant, it's the advanced water treatment plant. So we knew it would take that our regulations are set up where you can have direct sewage go through the advanced treatment facility and go right into the distribution system for people's drinking water. So that's where we had to concentrate, and then we moved backwards because there's probably aware of the surface water treatment plant. We allowed 2 logs of cryptosporidium treatment capabilities, 3 logs of D.WRE, and 4 logs of viruses. But again, as I said, we're not just a chlorination facility, a chlorination facility, so we had to draft these regulations knowing those are possibilities of the kind. Next slide. So this is just kind of a general overview of the regulations themselves. We didn't count them up. There's probably over 40 pages of regulations, very detailed. There's 24 separate sections. It's found within Title 22 to the Code of Regulations, Chapter 17 under Surface Water Treatment, and Article 10, which is the Direct Potable Reuse Regulations, like sections 64669.00 through 64669.30. And you can see this is not an exhaustive list on the screen. There's quite a few different components of this regulation. But one thing for certain is there's lots of plans included in this. We have an operations plan requirement, monitoring plan, safety water plan, joint plan, strategic asset management plan, optimization plan, method validation plan, and corrosion stabilization plan. That's along with the engineering report and TM demonstration. So quite a few plans required for this rule. Some of you may be aware in drinking water, which usually meet up with an engineering report, may require an operations plan. We usually do. And that's pretty much it. So this is including a lot of new plans into it. Something it's not new, but we're really going to emphasize. We went into some detail on TMF requirements here, and the Division of Drinking Water and State Water Board is looking at developing technical, managerial, and financial regulations. What's the water, wastewater industry, planning, infrastructure, and operation well to the future is something that's lacking, especially in the smaller mid-range utilities. And this, for direct potable reuse facilities is something just couldn't allow house. Those things have to be in place, and we have to have the utility of different is willing to fund this well into the future and keep it operating. Next slide, please. So two of the larger sections of the regulation are pathogen control. Next slide would be chemical process control. It's found in 64669.45. There's 7 pages of regulations text just on pathogen control. We talk about log reduction requirements for virus, Giardia, and cryptosporidium. Will require a minimum of 4 treatment processes for each pathogen. The minimum that you'll get, that each process must get a minimum of 1 log reduction. You'll get credit to 6 logs of activation for pathogen. 3 separate diverse treatment mechanisms for each pathogen. One will be membrane, one will be chemical, and one will be UV. And there'll be allowances for, you know, for new technologies. You'll have to there'll be validation study requirements for determining how much log reduction that each process will get. We expect engineers who are familiar with recycled water, wastewater, water treatment to be part of the development of these projects. There's going to be continuous process monitoring throughout. I think surface water treatment plants have a lot of monitoring. Different facilities will require a lot more monitoring and tracking. The requirement is design requirement will be 20 log virus inactivation, 14 log Giardia inactivation, 15 log crypto inactivation. The operation of the continuous operation will be 16, 10, 11 for the same constituents. There'll be requirements for 24-hour notification, 60-minute notifications during failures. There'll be lots of failure analyses and SCADA requirements, systems such as this. The next slide, please. So then the chemical control is found in section 64669.50. There's 10 pages of regulation text. So again, continuous treatments required. 3 separate treatment trains, the ozone followed by biologically activated carbon, reverse osmosis, and advanced oxidation requirements. That was one of the contentious points of industry versus the expert panel. They just felt that ozone needed to be followed by biologically activated carbon for it to be effective for chemical treatments. There is blending allowed. Ozone BAC requirements will be surrogate. Instead of looking for all chemicals, there will be a requirement for a log reduction for formaldehyde, acetone, carbamazepine, and sulfamethyl oxazole. And there will also be TOC requirements, empty bed contact time. So, and then the chemical control also will have to be validated through various studies, and all the requirements for salt rejection, permeate recovery, things like that. And then just on to the last slide. It was just, if you have any questions, here's where you can find more information. And again, we're just waiting for the Office of Administrative Law to finish up their review. Hopefully we'll be ready to put these out October 1st. And that's it for me, Karen. That's not it. Val. Thank you.
Thanks, Robert. So we're going to hold off questions and answers until all 3 presentations are done. And also, if you can just go ahead and, if anyone have questions, we can look at the chat box, send the questions to the chat box, or we can do it audibly. So let's wait. So thank you again, Robert Brownwood. Let's look at what the perspective from industry is. And Dr. Val Frenkel, he is the Vice President of Process Engineering at Greeley Hansen, a TYLin company. Val has 30 years of national and international business development, management, and technical experience, and deep expertise in water and wastewater treatment, water reuse, desalination, and of course, membrane technologies. Val is recognized as the expert in diverse experience.
I feel good. Thank you, Lynn. Yes, we know well that that regulation, if one of the major, or even probably the major driver in the water reuse. We all know that. And let me just share the industry perspective on the reuse, and particularly in focusing on the direct potable reuse. The regulations just came over end of last year. We just 7 months down the road. We all know, just let me just please back a little bit, step back for a second. So we know that reuse, we have a, from the industry perspective, we have a non-potable reuse, which is traditional reuse, known for centuries, and a relatively new concept that we called it potable reuse. And actually several or not several, but many places, the indirect potable reuse as a default is already existed. We're just acknowledging that now. Can we flip to next slide? On non-potable reuse, those are listed here on that slide just in the black fonts. If you may notice in the brackets, it's shown that actually the all non-potable beside the industrial, they are periodic or seasonal. So in other words, that only the industrial can be continuous. So what that means for the industry, that significantly increased cost of the project, because the reuse beside industrial, the non-potable, those are conventional reuse that we apply all over, it doesn't have the need year round. And what that means, that increased significant the cost of the project per gallon of produced water when we consider the non-potable reuse. And if we will take a look, then potable reuse, which is highlighted here in the red fonts, both indirect and direct, they generally the continuous both. So that actually improves significantly economics of the reused water. So that is from financial standpoint. If we go to the next slide, actually it's quite similar that what Robert already presented. Sorry. And on a non-potable reuse, just wanted to skip the slide. Generally, now can we go back for a sec? Yes, on one of the major regulatory documents, Title 22, very well known for reclaimed water, and it's actually in California. It's constrains or regulates two major parameters: the pathogens and turbidity. As soon as we're reaching those two criteria, depends on the type of the reuse, as listed here. This is the snapshot from Title 22. We can use that water for non-potable applications. If we go to the next slide, which is quite similar that what Robert already presented, the major difference between indirect and indirect, indirect potable reuse, we have the environmental barrier. It could be the groundwater, it could be augmentation to generally source of the potable water, as Robert already presented. And if we go to the next slide, the all difference between indirect and direct. And direct, we have a just man-made buffer or barrier, or we may even not have it. We may supply that highly treated water, wastewater, from the wastewater treatment facility or resource recovery facility, or to the source of the water, potable water, or direct augment the supply or treated already that water, and that's how the different projects are considered to be developed. If we go to the next slide, the potable reuse, actually direct potable reuse, the framework already were developed quite more than 10 years ago. And here I just want to compare the Texas versus California. So those two major documents were developed, and the rule, the Texas is considered 1086. It's viruses, Giardia, and the LRV on the finished water, and the crypto. So those three numbers, as you can see, if you go to the California on the next slide, it's a way more tight regulations. So you can see the number much higher. So we in California, we are more conservative to regulate the potable reuse. And again, we generally first who adopted the direct potable reuse regulation 7 months ago, a little bit more, little bit less than 7 months. Actually, most of the regulation and water reuse in California released last day of the year on December 31st. But that question not to me. Maybe Robert can shed some lights. Let's go to the next slide. There is the indirect already considered and being developed in many places or several places. In California, the IPR in California, the direct, if we go to the next slide, in San Diego area. And if we go to the next slide, the difference, actually, there is no crystal ball. But here's the some criterion difference in similarity between indirect and direct, if we will consider them. And it's quite interesting that economically, I don't want to take too much of your time, that will be recorded. You can look those, that evaluation. It's quite interesting that economically, direct potable reuse makes probably more sense. It may more challenging the decision by regulatory agencies, and I'll talk about that in a few more slides, the reason for that. But generally, as a capital, it direct makes probably more sense because we treat in water to the highest quality in many places or areas, a higher quality than source water from the potable water plant. And we, in indirect, we blending that water with natural water, groundwater, or some surface water, whichever the barrier is. Actually, we're polluting that water and we're retreating it again instead of using it directly. Again, this is from purely technical and economical standpoint, but there is several other aspects around that. If we go to the next slide, I would like to summarize the industry perspective on direct potable reuse. So first, we already talked about regulation already adopted. That, here's a, sorry, it's typo continuous. So it's more challenge on the public acceptance. It's precedence project. We need to build more confidence, and that's how the public will be accepting that public probably acceptance. I would, I don't know, interchangeable with what will be the first, the regulation already in place. The public acceptance, I would think this is the major priority. Economics, I already talked about that. The challenge is the actually operational experience, operator skills and training, and operator certification. This is quite important. And a risk associated. And if you will take a look at direct potable reuse, the major concern, or not concern, or major target, actually it's two parameters. Actually, it's relevant to both indirect and to direct potable reuse, but for direct, I think it's more important. First, it's a continuous monitoring and controlling of the produced water quality, make sure that it's in compliance continuously. And second, the measure is the response time in terms of any upsets or any red flags. If we will confidently can build the facility and build the project and make sure that those major criteria, I'm not talking about rest, there's several others definitely, but those the measure met, that will open more doors for the direct potable reuse. And as already Les mentioned, yes, we need more reuse water, direct, indirect, and California actually in a front runner on introducing those as a regulations. Thank you. Back to Les.
Thank you, Val. Well, next up, Dr. Leila Khatib is going to talk to us about antimicrobial resistance AMR testing in wastewater. I will let her educate us all. And there's going to be a pop quiz afterward, of course.
Of course. As always.
Hi, Leila. Thank you for
Hi.
doing this.
Thanks, Les. So today I want to talk a little bit about antimicrobial resistance and how it relates a little bit to direct potable reuse. I'd also like to acknowledge Dr. Sunny Jang, who's at the University of California, Irvine, who provided some of the, one of the figures and some additional information to support this particular presentation. Oh, next slide. The reason antimicrobial resistance is actually a concern is because about 2.8 million Americans annually acquire antibiotic resistance bacterial infections, and it leads to about 35,000 deaths annually. Now, wastewater treatment plants do have common antibiotics in their systems, and usually it's wide spectrum, some kind of antibiotic that's present, and they're usually there to treat respiratory and urinary tract infections. When they're in those treatment process in the treatment plants, they put pressure on the bacteria to maintain these genes and this resistance for survival. Next slide. So the next slide. So the way AMR is maintained and is disseminating within a wastewater treatment plant is through either horizontal or vertical gene transfer. So for horizontal gene transfer, bacteria are promiscuous. They like to swap genes with other bacteria to see if they can survive better than the next guy. So one bacteria and their friend next door, they'll just swap genes, and that's how they get transferred within a wastewater treatment system. They also can go through vertical gene transfer, which is you have one bacteria, and when they replicate, their progeny then has those same genes and carry it with them. There are two different types of genes basically within the wastewater treatment plant. There's internal genes and external genes. So the internal genes are associated with bacteria that are still intact. Usually those can be precipitated out, flocculated, they go down into the biosolids. Then you have external genes, which are kind of in the supernatant and the effluents, and those are present because the cell has decayed. And so now they're present in the substrate. So the next slide. To monitor these particular genes, of course, and this particular trait in bacteria, it's the standard methods that you've normally seen. Culture methods for coliforms, there's molecular-based methods, and we use surrogates to determine if an antibiotic-resistant gene is present. The common ones that are being looked at are class 1 integrons, and those particular ones mark horizontal gene transfer within a wastewater treatment plant. You also have beta-lactamase producing Enterobacteriaceae, and those particular ones are kind of going to are starting to become the ones that people are thinking are the coliforms to look for AMR monitoring. There's other types of genes out there that I've touched upon, but we've also have metagenomics, which is next-gen sequencing, and the current thought, because people are using different methods to for surveillance of AMR and wastewater treatment, people are starting to go toward, or researchers starting to go toward, antibiotics resistant gene copy per number of cells as a way of standardizing to compare between wastewater treatment plants and the presence of AMR. One of the biggest gaps we have right now for monitoring is that it's difficult to compare. And we know that there is variability in geography, seasonality, monitoring methods, and that variability, we can't really do comparisons unless we have a standardization. So the challenge is to standardize towards stewardship. And these are some of the methods that we're using, that are being proposed today for monitoring. Next slide. So beta-lactamase producing Enterobacteriaceae are actually a resistant bacteria that is known to occur worldwide within wastewater treatment plants. So it's being looked at as, is this a possible indicator that can kind of capture everything about antibiotic resistance in wastewater treatment plants? It's a coliform, so coliform testing works. It's in all wastewater treatment plants, and it connects the food and water and environment because this bacteria does not really occur in pristine environments. So if it's in the water, the food or environment, it usually came from a wastewater treatment plant or some other source of human origin. There is seasonality they're finding, and the abundance in different wastewater treatment plants varies greatly. So next slide. In terms of wastewater treatment plant and AMR, there's a few studies out there, and there is a large variability, again, because standardization, we're in comparison. So we look at the studies, and it's kind of a once, and how do we compare it to the next? Well, in terms of activated sludge, it really says that this study showed that there was really not sufficient removal of AMRs, particularly because of the extracellular ones that's floating free without cells in the effluent. Tertiary treatment, they're reporting 3 to 4 log removal. Additional studies that haven't been published yet, they're showing a 20% reduction of antibiotic resistance genes and virulence factors across the entire treatment process. However, this study is also showing that there could be enrichment in the secondary treatment. So, that horizontal and vertical transfer where you're producing more progeny, and the pressures of those antibiotics in the wastewater treatment plant are allowing for these traits to actually increase because it confers survival. So they have these traits to survive. So more of those bacteria are surviving. Metagenomic analysis of the 450 samples is also showing there's a lot of seasonality with these traits. Obviously, people get sick at certain times of the year, or there's something is going through the population, so we'll see some seasonality. One of the biggest gaps we have right now is also the role of the different treatment processes to remove AMRs for direct potable reuse. And the reason this is important is if you're a large city or municipality, that's great. You can afford to buy the biggest treatment system you can buy. The smaller and the mid-size, we want to know where is good enough. How is good enough at secondary treatment, or do we need to go further for that, to use these as direct potable reuse? And how far can we, where is our kind of minimum treatment where we're being effectively removing that? Next slide. In terms of the current treatment methods out there, of course, BNR and any kind of nutrient removal system will remove these particular types of genes and proteins that are associated with antibiotic resistant bacteria. However, this concept of balancing removal, energy, treatment times, and technology is something that needs to be addressed as well. So something like Anamox, which is a treatment process, it works, and it's specifically for nutrients, which does it also still reduce AMR well enough? There are other things like some types of membrane treatments where you need a solids retention time of 300 days to get reduction. That's not feasible. It's academic, but it's not feasible. So there are balancing those different types of treatment technologies. Next. So one of the things that we also look for is tools for stakeholders. We have quantitative microbial risk assessments. How much risk are we actually going to take if we treat a certain type of bacteria and certain type of resistance? So we're looking at these ESBLs, which are kind of becoming the standard monitoring for antibiotic resistance. And we want to assess the risk of infection, because do you treat to a certain level and then we've reduced our risk enough? We also have people looking at artificial neural networks, AI. There's really non-linear relationships associated with wastewater parameters that we monitor and the presence of AMR and other factors in the wastewater treatment process. And we want to know if we use AI, what combination of these parameters will allow us to be predictive of the real risks associated with AMR? And I think that was my last slide. So a couple of ideas. AMR is seasonal. It's disseminated within the wastewater treatment plant, either through vertical or horizontal transfer. And we have very limited information regarding how AMR is reduced in the various specific treatment steps through a treatment process. Okay, thank you so much.
Thank you. Thank you, Leila. We should go to questions and answers if there are any questions. I'll wait, but in the meantime, I'm going to turn it back to Cameron or Scott for some concluding remarks on this meeting. Go ahead, Cameron.
All right. Well, thank you. That was very interesting. I'm still trying to wrap my head around some of the things you threw out, Leila. But that was very interesting to learn about potential, I guess, avenue to reduce costs and increase water quality. I guess the question I kind of had just thinking of the three conversations we had, and this is probably more for Bob, but Val, you might be able to answer as well. Does the State Water Board interact or fund research similar to AMR to explore maybe a lower cost option to make DPR more accessible?
Wish we did. It's in our statute that we should be doing research. We just don't get the funds to do it.
So I also have a question for Leila. Is CSUs or even University of California doing anything with artificial intelligence in maybe being more quantitative and maybe lowering the number of parameters that needs to be tested in relations to either IPR or DPR at the university level?
Well, we want to definitely do some more studies on some of those tools like quantitative risk assessments and neural networks. So we want to leverage AI to say, if we look at this parameter, we don't have to monitor everything. This parameter is really representative of other aspects of the waste treatment system. Will that help it? You know, we always are thinking, how can we not add more things to do for the day at a wastewater treatment plant when we're proposing an idea? Right now, we're exploring those kind of ideas. We look at different methods. Can we reduce? Can we look at many items at one time?
Mm-hmm.
You know, those are the types of things.
Okay.
What other new technologies can we do to not, you know, to use technology, but without technology? So kind of a concept.
Yeah, I also understand that as a hydrogeologist, we are looking into using AI to do more modeling of water quality and impaired groundwater. So for Robert and Val, I imagine AI will become very prevalent in the water industry. Right now, in the groundwater studies, we are much more into the rule-based AI, meaning we have a set of rules, we have a set of data to ask AI all sorts of questions. However, the world is going into generative AI. That means that external to the rule base, these questions will look all around the world in milliseconds to come up with answers. So we are very interested in either methods of AI to look at impaired groundwater quality. So that's the end of my comment. Thank you.
You know, let me add to that. It's a great, you know, development in the industry. Definitely, it's no question. But AI generally is based on a currently collected, I don't know, global experience, if I may say that. The area of the direct potable reuse and control of the water, it's a relatively new area. So, you know, it's I think it's still a way to develop new stuff in the concept. And I already, as I already tried to share for the potable reuse, the major constraints or challenges is the continuous monitoring and control of the water quality. and at the level and how in the water control you can't take samples periodically and control all characteristics. So it needs to be figured out what to control or minimum control to make sure that all constituents, other constituents of concern are covered if you meet in that particular criteria. Okay.
Yeah.
Like
Yeah, and
the-
I think also with AI, one of the things about AI and water quality is that we have to train it.
right.
And without training it, we have to have those databases. So one of the things we do is we go to Sequis and get all that data and train it. And then we go to US EPA ECHO and pull that data, water quality data, and train it. However, you know, some of the influence is missing. Some people aren't reporting. So those kind of things that are missing just from databases, or somebody puts in 1100 for a pH, throws off the
Yeah.
learning process.
Let me explain into the dynamic and gap of the results and data. So look what happened. If you just controlling your produced water out of the direct potable, you already may be late, right?
Mhm.
Because it's already going to the customers. You need to control the source to that produced water. In that case, you will have that time gap or response time. And if any change, to make sure that that change will affect, or the changes always occur. You can't enter the same water 2 times, right? So my point is, you need to be smart enough, and that AI can help there. But again, I doubt that we have a sufficient data for that today. So if any change occurs, make sure that they will change or not change the produced water quality. And that is, if it doesn't change, so you just keep producing the water. If your source changing and it may potentially affect your produced water, that you need to respond. So in other words, so if any change, you don't want to shut down your DPR supply all the time, right?
Right, and you want to make sure that the AI predicts early in the treatment, so like the influent.
Right, correct, yes.
Not the effluent.
Yes.
And Scott?
Yeah, great presentations, everyone. One of the things I've always been interested in with any kind of advanced water supply ideas like this, whether it was managed aquifer recharge, DPR, has to do with geochemistry and monitoring. Geochemistry is going to change whenever you mix different water types, when you have a new water type with a different infrastructure, et cetera, which can cause different types of reactions that may be problematic. We can model that, we can do calculations and for expectations, but to me, the monitoring is still the Achilles heel. And so I guess my question to the panel is, where do you see, or what do you see in terms of new research and monitoring, new techniques or plans or even placement, of different types of monitoring device that might feed into an overall, data analytical system, and then be available for, the segue back to the conversation you just had into the AI world, so that we have this information.
So in terms of my personal opinion on this is that there are places that are looking at real-time detection, because PCR is delayed, culture systems are delayed. Next-gen sequencing is really, really fast, but the expense is a little bit on the higher side. So I don't know if it's feasible for wastewater treatment facilities on a daily basis, especially small ones, to do it. And then it's also based on nucleic acids. So next-gen sequencing is a nucleic acid test, which doesn't tell you live or dead. It just says the gene is there. And does that mean anything? So there are systems now, people are looking at flow cytometers. They're looking at, which is very expensive and very labor intensive and requires a lot of training. But there's also microfluidic systems that people are looking at as well for monitoring. So there's a variety of different systems, but a lot of it is based on how well the treatment system works. there's a lot of focus on that right now.
So it sounds like an area of research and opportunity, I
Yes.
guess, right? That's where a lot of new ideas, different types of, real time versus or indicators, if you will. If you can't get the real time direct, but have enough information that if you see one thing, you're going to expect that there's something else you have to be watching for.
Yeah.
We took that kind of into account with our regs, looking for those 4 chemicals to make sure your RO system works properly, advanced oxidation works properly. Yeah, Leila was totally correct. Flow cytometry, that was suggested to us, and we did research that and talked to some of the manufacturers who make it. They're just not ready for it, like real time. Even those have a 20-30 minute delay. Even though you think you're taking it, the camera, you're actually taking a quantity of fluid. You got to prepare it, then you got to run it through the camera, and after that, you have real-time data that's still 10 to 30 minutes already passed. And if you're doing, 120 million gallons of water a day, that's a lot of water through that 10 to 30 minutes.
Yeah. No, I was thinking of even things like if you're looking at other types of parameters, like some of the inorganic chemistry, metals, et cetera.
Right.
We have some real-time devices today that are available using different electrodes and all that you can actually build into your system. Again, the water rate and the water flow, I think the volume is the challenge on some of that. And then what does it mean, right? To a whole set of very, nuanced parameters, for example. But
when I had 3 questions for Dr. Khatib and one for Val. So on the AMR, did you find that it's more difficult for the same treatment that's treating non-steroid bacteria versus the steroid? I look at almost Schwarzenegger type bacteria. Did the process treated both identically, or did the AMR bacteria, are they more robust and get through big?
Identically, similarly. Yeah, I don't want to say identically because bacteria is bacteria. Bacteria, that any treatment it's actually size exclusion, right? Even on a dissolved level, so that you have certain rejection percent depending on what type of the treatment you're using. And if you're using RO as an example, depends on type of the, so it's blind bacteria within that range. So the classification with the smallest are viruses, next bacteria, and the largest the protozoa.
And then what kind of pathogen loads are you seeing out there when you do? You say 20% removal or whatever.
On a pathogen?
What were the loads coming in?
As a bacteria, practically RO removes, if I may say that, 100% if there's integrity.
No, raw sewage. Yeah, coming in raw sewage.
Pardon?
What are you seeing in the counts? What numbers are you seeing in raw sewage?
Oh, it's a millions. It could be. Yeah, it doesn't matter because that it's more concern the biology of water, because if you're using RO, it's a more the fouling, biofouling may be concerned, but not the number of the bacteria. No.
Is anyone looking at fungi? Are we just ignoring fungi completely in wastewater treatment?
Yeah. No, but whichever is proposed, as you may know, that there is the RO and non-RO type of the concept generally proposed. And as a RO, it's usually include the low pressure membranes followed by high pressure membranes by AOP. So, and that actually it's a good marriage because the RO addressing the bacteria and everything, whichever the largest size, the fungi and the protozoa. And with viruses, it's a separate discussion. However, the AOP can well take care of the viruses. As you
Leila,
may,
Leila, do you have anything to add to that?
No, that sounds, that sounds.
Okay.
I'll get it right.
No. Leila, please add. I would love to hear you.
I guess we're not going to have a pop quiz on this one.
No, I'm being, no, I'd have to look to see the exact, but it's like every other raw sewage that comes in, it's millions.
Yeah.
Scott, do you have any other questions? You're the expert on water quality here. So.
Well, no, I mean, I think this is fascinating, really interesting, and I think there's going to be a lot of, communication to me always is one of the hardest parts, right, to the public and to the users, and because there's a lot of, as we're talking here, there's a lot of really deep scientific work and analysis that has to go into this, and that's a very difficult thing to explain to the public at large. Maybe that's a good ending type question, is how do you see the communicating this? And I mean, the water board to the academics, that's a tough job, and wondering how you're feeling about that today, recognizing that there's a lot more we know, but there's still a lot that we're still, trying to develop information on.
Scott, the biggest challenge, it's the public acceptance. In the
Yuck factor.
Yeah, regulation already in place, at least in California. And plus, like any new concept, usually the people are conservative and the yuck factor. But like any new project, the more project will be developed and proven, the more precedents will be built historically, the more that will be adopted and will be developed and disseminated around the states.
So the next
that
question,
takes time.
Then I do have a question for Robert. So how are we going to advocate this to end users? I still remember managing SFPUC's groundwater blending into the HHE system, and people were just saying, I'm not drinking groundwater. That's not even the yuck factor. That's just groundwater. And also, then second part of my question is, how are we going to ask, Gavin Newsom to allow for more funding for D.WRE to do work on this?
Yeah, that's the cool thing. That's your guys' job. I mean, we wrote the regulations. We try to be as protective of public health as possible. That's kind of why, the science to back up. I know some of the argument was we were too conservative on our numbers, and that's in the past. The numbers we have, but the more science can show, they were conservative, but we're providing water that it's not going to cause anyone sick or any diseases. But that's up to the utilities and you consultants to figure out. We're not social engineers. We're not. That's a great question. I think Scott was right. That's probably your biggest hurdle, is for how to tell the public. It's the science. My old mentor, Harvey Collins, said it doesn't matter how great your science is, if you can't convince the politicians and the public, that's because the science is going to sit on the shelves. So.
Yeah.
On funding, I've been asking for that my entire career. It's probably so have all you. It's just something that research is. We're always looking for money for research.
Well, thank you all. Back to you, Cameron.
Yeah. All right. Well, thank you, Val, Robert, Leila.
Thank you. Thank you all.
It was a very productive conversation. I will be sending out a recording at some point, probably tomorrow. And if it's all right with you three, I will include your emails. If there are questions, they can touch base with you, or I can assist with kind of connecting everyone. But yeah, again, thank you for joining us.
Yeah, thank you all. And
thank you all. Thank you.
Yeah, I know it was a smaller crowd than we often have sometimes, middle of summer perhaps, and things are going on. But what often also happens is that once the recording goes out and the email goes on, people say, oh, how come I wasn't part of that? And we get a lot of feedback that comes back later and requests for, interaction with each of you. So we're not done yet. Just because we only have this 1 hour, it's a continuation of the whole
The X
program.
factor, they all
Oh,
talk is TY.
But would we need to regroup again?
Maybe, yeah.
Actually,
Absolutely, Val.
Okay,
all right.
okay.
Well,
Thanks,
thank you,
Leila.
everyone.
Thank
Have
you
a good
all.
night.
Thanks, Robert.
Thank you.
Good to see you.
afternoon.
Thank you.
Bye-bye.
Bye-bye.
Bye.